All right, so in this video, we're going to look at properties of water. We're going to look at the actual structure of a water molecule first, and then talk about how because of this unique structure, it has some unique properties and how it's essential to life. We know water is essential to life because when we look at this emerging field of astrobiology, so looking at life on other planets, one of the things that NASA and other people get most jazzed about is when we can find evidence that a planet had liquid water at one point. And this is true of Mars. There's been fossil evidence that have been pulled back that people have indicated or pointed to as evidence that liquid water, existed on that planet. And that's because we don't know of a form of life that can exist without liquid water. Do this in class together, so skip it for right now. And let's pick up on your notes. So in terms of looking at the structure of a water molecule, water is H2O. That's its chemical formula. H2 tells me that I have two hydrogens. So if I look at my diagram right here, it's a little bit in the red, but that white circle right there, just like in our ball and stick model, is meant to represent one hydrogen, our second hydrogen, and then O. I have one oxygen, which is this red circle here. And I notice that water is bent, so it's kind of like a really wide V looking. So that's what it looks like. In terms of how it behaves, what the most important characteristic of a water molecule is that it is polar. Now, when we call a molecule polar, we're saying that the atoms within it, so in this case, my hydrogens and my oxygens, are sharing electrons. That's how they're bonded or connected to one another, but the sharing is not even. So imagine in this instance, you think of the electron, so the subatomic particle that's actually involved in the bonding is like a rope in a tug of war. You have one atom that would be like a very strong person and one atom that's behaving like a very weak person in this tug of war. So one of them is actually getting more of the pull on the electron. The electron is physically spending more time around the nucleus of that atom than the other. And because of that, we'll see this with water in a second, as the electrons begin to congregate or hang around just one atom, they're going to concentrate the negative charge. And so that atom is going to start to behave as though it is negative. And since the electrons are spending less time around other atoms, that atom's protons or positively charged subatomic particles in the nucleus become exposed, and that atom will start to behave as though it is positive. Now, the important distinction for us here, and what we want to have in our notes, is that water is one of these molecules that has that negative behaving piece and positive behaving piece, but it is still a neutral molecule. What I mean when it's neutral is I mean it's not an ion. It hasn't totally lost or gained electrons to have a full charge. And I know that because if I count up the number of protons, so 8 from oxygen and 1 from each of my hydrogens, so I have a total of 10 protons or pluses, and then my electrons, 8 from oxygen and 1 from each of my hydrogens, 10 electrons. So I have 10 protons, 10 electrons. They're equal. There's no charge on this molecule. But those 10 electrons spend way more time hanging out around the oxygen. And that's because remember, oxygen has 8 protons. It's got 8 positive charges pulling on those electrons and attracting them. So this this part of the molecule is going to behave as though it's negative. And my hydrogens down here, since their electrons kind of ditch them, you just have their protons in the nucleus exposed. So they're going to behave as though they're positive. Now they're showing you this charge differential right here in color. So the top, the dark blue up here, is meant to represent where a lot of the electrons are clustering. So that's that negative charge. And the red down on the bottom here is representing where you find your electrons least often. So that's going to behave as though it's positive due to those exposed protons right here. So neutral, protons equal electrons, but electrons not evenly distributed. More around the oxygen, oxygen acts negative. So big idea here, oxygen is slightly negative because of that concentration of electrons around it. Hydrogen acts slightly positive. This allows water to act like an ion. It behaves as though it's charged, even though it's not. And in terms of symbology here, so this right here, this thing that looks like an unfinished figure eight, this is a sigma, and this is what you use in chemistry if you want to denote a partial charge. So the fact that it's around the oxygen here tells me that oxygen is partially negative, acting as though it's negative. And my hydrogens down here are partially positive, acting as though they're positive. Basic rules, because we're going to talk about how water interacts with other water molecules. Remember, chemistry, a lot of times intermolecular forces, reactions can be explained just by kind of thinking about what we know about magnets. Opposite charges attract, like charges repel. So what we find is that there are different types of bonds that we find in our water molecules. It is covalent bonds that hold together the oxygen and the hydrogen in the same molecule. So for example, in H2O, the two hydrogens are connected to the one oxygen through a covalent bond. They're sharing. We have a second type of bond, and this one's totally new for us, called a hydrogen bond. Hydrogen bonds are these incredibly weak interactions. They really shouldn't even be called bonds that occur when the negative oxygen from one atom is attracted to the slightly positive hydrogen from a different atom. So remember, think back, previous slide, opposite charges attract. So if I have two water molecules right next to each other, well, then the opposite charges on those water molecules are going to attract to one another. And that attraction, that slight attraction between those partial opposite charges, forms these weak interactions we call hydrogen bonds. And frankly, it's what gives water most of its really cool and unique properties. And I'll talk about what some of those are in a second. So if we want to visualize bonds right here, so here's one water molecule. I have oxygen, two hydrogens, and remember these gray lines right here, those are the covalent bonds, strong bonds made by sharing of electrons between oxygen and hydrogen. So here's one molecule. And then over here, a totally separate molecule of water, one oxygen, two hydrogens covalently bonded together. But remember, this oxygen has a slight negative charge because all the electrons are hanging out around it. And this hydrogen has a slight positive charge because its electrons all left it to go hang out with the oxygen. So positive, negative are going to be attracted to one another. And this dashed line right here across the middle represents the result of that attraction of those opposite charges. That's your hydrogen bond. And again, it's much weaker, but it still absolutely gives water some unique properties. So we're going to skip this for right now. We'll do this in class together. But this idea of hydrogen bonding, you guys are actually going to see this in your lab, and it will help you to understand kind of some of the unique properties. You guys will actually do a lab portion on surface tension and looking at this water strider. All right. So now we're going to take this idea of water's polarity, its partial charges, and the resulting hydrogen bond, so those weak attractions between molecules because of the partial charges. We're going to answer this question. Will it mix? So we're going to try and figure out what types of substances will mix in water and what types won't based on using the structures. I'm going to pause here for video 2.